quantization of the first part, and maybe like to make it more precise, the deformation quantization. Right? I think tomorrow morning we're going to have a lecture series on geometric quantization, and today it's one of the many approaches to deformation quantization. But here I will have to start with an aside, with a reminder, or maybe telling you an approach to quantum groups due to so-called FRT, Faddeev, Reshetik, and Takhtajan. Because it introduces the right notation and it introduces the way to present the quantization scheme for co-crossed brackets. So first, maybe a rather general idea. Suppose that V is the vector space and curly A is an algebra. So kind of we're going to be using I don't know how I noted. We're going to be using objects of the type elements of the tensor product of endomorphisms of V times an algebra. So this means that in practice this U is a matrix, and in that matrix elements are elements in your algebra. So, in particular, suppose you have two copies. So that's a little bit similar to the story of the classical Yang-Baxter equation that we had before. Suppose that now you have two copies of V, and we take a tensor product of them, and we have endomorphisms, and we still tensor with A. So here we can define the following objects. We can have, let me start with U2, this is 1 tensor U. Right, so we take U which lives in endomorphisms of that V, the second V, and in A. And now, for the same reasons as before, I don't write U1, because here you need to put the part which lives in endomorphisms in the first endomorphism, tensor 1, tensor A. So that's a bit similar to what we were doing before. So now, the following remark. So assume that we have R the quantum R matrix which quantizes the classical R matrix that we have chosen before. What does it mean? So typically this means that R is a function of a parameter Q, or sometimes people prefer to denote Q as exponential of H bar, and it is equal to 1 plus Q minus 1 times small r plus O of Q minus 1 squared. Or you can replace Q minus 1 by H bar if you want. So that's the first condition. And the second condition, you need this R to solve the so-called quantum Yang-Baxter equation, which is R12, R23, R13, R23 is R23, R13, R12. I hope I write it correctly. Certainly 30 years ago, that was a very easy task. Now, so that's a multiplicative analog and maybe more beautiful analog of that equation there. It's some kind of version of a braid relation. You can recast it as a braid relation if you want. And why are we focusing on that? That's because the theory of quantum groups essentially gives us solutions of those problems. So combinatorial quantization takes in the definition of a quantum group. So we assume that we know how to do it. If we don't know how to do it, like, the story does not quite make sense. So we're assuming that we know how to quantize the classical R matrix, which was used in the four-crossly formalism. So this is our assumption.
Maybe I should have asked this the previous hour. Do you have an example? Is there a way to write an R matrix for like the classical one?
Yeah. Let's write an example, but don't ask me to write in the general case that example. But let's write some. I actually prepared some small examples. So maybe for GLN, an example of small r to start with. So to start with,
quadratic Casimir.
No, not quadratic Casimir. No, but look at it. Stare for 2 more seconds. It's not a quadratic Casimir. Because right here I have 1/2, and here I have I less than j, right? It's not really. But if I add R12 plus R21, then I get quadratic Casimir, but maybe I should have got twice, here this, okay, we don't settle this 1/2 issue. Okay, now an example of capital R. Now capital R should be a 4x4 matrix, right? It acts in V times a V. Probably, as I say, probably many of you are much better experts than me in this. Sorry. So I copied it from one of my old papers, and in that paper I certainly copied it from some classical papers on those R matrices. So that would be a quantization of the n equal to 2 case, and a very famous one which goes also into some whatever 6-vertex model or whatever it is. Right. So we assume that we have a gadget like that. So this is one big thing. Now, what about this FRT? So I want to give you 2 examples.
So can I take the rational solutions too, or do I have to stick
Sorry?
Can I take the rational solutions too, or do I have to stick with the trigonometric solution of the Young vector?
Wait. No, but I mean, okay. So this is just constant, right? There is nothing rational or trigonometric or elliptic about it, right? So this guy doesn't have any spectral parameter, just maybe to make it, because you probably are referring to a wrong intuition, right? So there are constant R matrices which correspond to like finite dimensional quantum groups, like UQSL2, right? There is an R matrix. That's the R matrix in the fundamental representation of UQSL2. and it's completely finite dimensional. But then there is the whole story in integrable systems, quantum integrable systems, where you have R matrices with spectral parameters. And there, what you're saying, the dependence on the spectral parameter can be, as you said, rational, trigonometric, or elliptic. And here there is none.
Thanks.
Just to. Okay. So maybe one more remark here. Once you have an R matrix, let's call it R plus, there is a system R matrix where you take a permutation operator between the two copies of your V, and here you take R plus inverse and you take another permutation. So this is also a solution of the Yang-Baxter equation, and we're going to use both. So this is always like with one comes the other, like automatically. Right. So now I want to define for you two algebras using this R matrix formalism of FRT. So one algebra that I want to define for you, this will be very closely related to UQ of G. So in fact, there will be a map which is not quite an isomorphism, but which is close to isomorphism from something which is called loop algebra. And here there would be, quantum groups. They always come in pairs, right? These are Hopf algebras, and you can consider the dual Hopf algebra. So the dual to this one, these are so-called quantum functions on the group, right? I don't know whether you people seen it, but there are always like pairs. I actually don't need this guy all that much, but it's easier to define it. That's why I want to give you both examples. So suppose now we put our V to be Cn, so n from our GLN or from UN. And let's define an algebra by the following set of relations. You see, recall that U are matrices, and their matrix elements are generators or are elements of our algebra. So, and this is a set of quadratic relations. So a priori, I have generators and I have relations. So it defines me an algebra. Of course, to understand what those relations are, it takes a lot of effort. I wrote some example. So if n is equal to 2, I can say this U is a matrix ABCD. So my generators are ABCD. So this func U of GL2 is an algebra with generators ABCD. And now I should determine what are relations. Well, so one needs to write down this stuff and relations will come out. Maybe I write some of them, they will be something like this. AD is equal QBA, AD is equal to DA, blah, blah, blah. So if you want, you can take an exercise, right? This is an explicit exercise. You know R plus, you take those ABCDs, and you write those relations. There will be 16 of them, because, right, these are 4x4 matrices. There will be 16 matrix elements. They should be equal on the left and on the right. And they're not going to be all independent. I think in the end there will be, I don't know, 6? Yeah, I was thinking to ask you. Yeah, there will be 6 independent ones. So, but maybe we are somewhat more interested in this UQ of G. And here, let me maybe denote it in a different way. So U and let's say W will be still an element of endomorphism Cn tensor UQ of G. And the relation is as follows. Sorry for torturing you with that, but unfortunately there will be more stuff like that. So I want you to recognize at least a little bit, like kind of what it is. And here the relation is this. Again, at some point I was crunching those relations every day, several hours, but now, well, and you understand why I kind of tried to forget. Right. So this is a rather famous equation as well. So this is a famous equation. Usually, I think the traditional notation was not U but T, and it was called RTT equal to TTR. This is some kind of whatever signature relation in this FRT business, and this is called reflection equation. And if I'm not mistaken, maybe that's this way that Kulish and Reshetikhin first discovered UQSL2. So UQSL2 was discovered before other quantum groups, and so I think maybe that was the original motivation. Now, let's say I want to still give you one example. Suppose that G is SL2, and for UQSL2, many of you have seen the generators and relations. So the generators are denoted E, F, and K. K can have positive or negative powers. Maybe I don't write the relations of UQSL2. Is it okay? And but what is this matrix W, right? It's a 2x2 matrix which looks like this. Again, well, no guarantee that my formulas are correct. Valerian, what do you think? Is it plausible?
Yeah, plausible, definitely.
Okay. That's very soft way to put it. So you see that's this is, let's say, in a first approximation at the level of precision at which we are currently, we can say that this map is almost an isomorphism. So you probably need to take some square roots of generators if you want to go back, which means that, of course, algebraically it's not quite an isomorphism, but it's close to being an isomorphism. So in any event, you can think of this story as a working approximation of UQ of G.
Sorry, what's the relation of this W to AL plus and AL minus? Is it something like AL plus and minus inverse?
Yeah, it's like L plus or minus inverse. Yeah, sure. Right, sorry. Again, I should have denoted by L, right? Not to confuse you and other knowledgeable people. Yeah, I think, yeah, you're right. The usual notation for this guy is T, and the usual notation for that guy is L. That's true.
So is the claim that this RUU relation goes to the Fock-Grosley?
Wait. So that's the content of paragraph 2.2. Yeah. Of course, we do it for a reason, and the reason is we now want to quantize Fock-Grosley, right?
I'm sorry, can I ask something a bit independent? Suppose instead you have G, if G is, a Poisson-Lie group, and you want to consider the dual Poisson-Lie group, and then function on that, so you also have the duality like on the semi-classical level. Yeah. How does this mix up with this?
No, but these are two dual Hopf algebras. Of course, right. I only told you the relations, and which means the algebra structure. I didn't tell you what is the coproduct, right?
Yes.
But then
Yes.
eventually the coproduct of this one would be dual to would define the product of that one, and the other way around.
Okay.
So the product of this one is a very easy thing. It's just a matrix product. So of course these are two dual things, and as I say, I'm more interested in this one. That's because now I want to restrict the presentation a little bit. In the full four-crossley story, this one would also play a role.
Okay. But so if I do like function Q on G dual, that gives me back.
No, but normally function Q on G dual, depending then
Right.
on how you do it, but normally that should be this guy.
Right. Okay. Yes. Okay. So.
And that you can argue whatever. You can have a let's say you can have several semi-classical limits of this thing. Maybe we can discuss it later in detail.
Sure, it's not.
And one of them would give you like u of g. Another one would give you functions on small g star, and yet another one would give you functions on capital G star. All right. So. Okay, so we are given a surface, right? Now we are back a little bit to the story of moduli spaces. Let me consider a surface with one boundary component. So that's just to simplify stuff. And in phi1 of the surface, I will choose a generating system, alpha 1, alpha g. Beta 1, beta g. So in particular, home phi 1g. So these are free generators of that group. So if I want a representation, I just need to give an image of each of them. And so an element here is just a 2G tuple of elements of the group, or in our case, simply a tuple of matrices. Now, here there is a distinguished element which corresponds to the boundary loop. Remember, we had long ago, last hour, we had some discussions of boundary loops. Now there is one boundary loop, and this gamma is equal famously to the product of group commutators. Right? Okay, very good. Now we have a Poisson algebra on functions, right? We have a four-crossley Poisson algebra. This tries to Poisson algebra on functions on the form, and we want to quantize it. Quantize it, this means we want to replace it by an associative algebra with a parameter such that when parameter goes to 0, the first order term would be given by this phi. So here is a concrete recipe how we can do it. So we define matrices AI, BI, but now in endomorphism of Cn, tensor semi-algebra, let's call it capital H. H, this will be quantization of the algebra of functions on home. And in the spirit of FRT, I want to define this algebra by quadratic relations in terms of those generating matrices. So the generators are matrix elements of those matrices. So relations. Well, that's probably the most painful part of the talk. Sorry about that, but it's not going to be very long. Still. So maybe before I do it, like let's say how does it work? I'm not sure I will be able to draw very well, but at least let me say. So this is my base point. So what's the order of the ends of those alphas and betas? Probably first goes out alpha 1. And then if you look at the standard books on surfaces, so the next one will be beta 1 and then it returns. Right? And then there will be the next pair, and then the next pair, and then the next pair. Right? So think about it. I think that's correct. So you have alpha 1, beta 1, alpha 1 returns. So you need to make an experiment with just a torus, with a boundary component, and that's how the ends will enter. So that's my linear order. Before I was writing linear order counterclockwise, but now I think, it goes clockwise. Sorry. I don't know which one is right. Okay. So now relations. So there will be three types. First of all, that's the reflection equation for any of those So X is any of those. So any of those matrices generates for you a copy of a quantum group in the first approximation, which is nice. So you don't need to look at this horrible formula, but this means you have a copy of UQ of G. Okay. Now the second relation. Suppose that you have X and Y, and this can be A or B, but they are from different pairs, and one of them to the left of the other. So whatever, X, left of Y. So then it will be something like this. So it will all the differences between those relations are those pluses and minuses. And basically it tells you that they don't talk to each other. Okay, I don't want to make it precise, so this means UQ of G. This means more or less they commute. Maybe I think one can say they commute in some category. So we have algebras with an action of a quantum group, and they commute in that category of algebras. So something like that. So, and finally, for completeness, I write for you one more relation. I think when those relations were written, this one was sort of new, but that was long ago. So relation 3. What happens if you have A and B from the same pair? See here there are 3 R pluses and 1 R minus. And that's unusual, and that's complicated, whatever. That's some kind of... Okay, so the claim is that this algebra quantizes the algebra of functions on home pi G in the sense of deformation quantization. So this is an associative algebra. Those relations are not self-contradictory. There would be some kind of PBW which says that that algebra has a reasonable, the correct size, and this is a quantization of this home. Now, maybe...
Can I ask, there's something fundamental I'm missing. So you're saying that if you look at liberation 1, then these things, each of those AIs and BIs give you UQ of G, right? But it would be more...
it's, you know, if you, like, you're now asking as a person from a public or as a refined and accomplished algebraist? Tell me.
No, I'm asking exactly, well, I don't know how to answer this question, but I can tell you what I'm asking. I'm asking about the difference between UQ of G and function Q of G.
Oh,
so I would actually...
enormous, right?
No, I mean, no, I understand, but somehow it's kind of looks natural because, I mean, space you're quantizing is G to some power. So like every factor, it would be natural to expect that every factor would...
So you pretended to be a person from the public. Good. That makes my life easy. No, but you see, G, that's true, but depends with what kind of Poisson bracket, right? So G carries several Poisson brackets that you can invent, and one of them is the bracket of the Poisson group G. Its quantization would be this.
Okay.
But then
you're saying that's not the one. That's not the
one. But then the other one. There is a map from G star to G, right? Multiplying the two components. And that's this one, which corresponds to UQ of G, right? So it depends what kind of Poisson bracket you put on your group.
So what is the map from G star to G? I mean, is it because G is GLM?
Okay. So let me write one magic formula that was already mentioned. I don't know whether it's going to convince. Right, the dual Poisson group is typically like that. You can map it to W, which is F plus or minus 1, which is a so-called Semyonov-Tinshansky map.
Okay.
And so this would induce a Poisson bracket on the group G, which is a target. So the image is dense, the Poisson bracket gonna extend, and this would induce for you a Poisson bracket on the group G. That Poisson bracket.
This version of UQ of G has the property that if you put Q equal to 1, you don't get U of G, but you get you get this.
Yes,
this
you're gonna get this.
Okay.
That's right. Okay.
So is the main thing that here we have interrelation A, B, A inverse, B inverse, and if we have just a kind of non-intersecting cycle, we correspond each of them to functions on G, right?
Wait, say again.
So we can draw it as a torus like this, but we can pretend that there are two holes in the sphere, right? And if there are two holes, there will be functions on G.
Oh, you mean if there are, but to have functions on G, you need two base points. You see that okay. You see, in principle, the rules that I announced before the break, they tell you the bracket in all possible situations. Maybe just a couple of words answering your question. Right, so those brackets, right, they have R matrices on either side. And basically it tells you that maybe, so this is something like that. Maybe that's a disk, you have 2 points at the boundaries, and that's your graph. The disk contracts that graph. So this is 1 point, that's the other point, and they correspond to those two R matrices. Remember, in the 4x3 formula, there was some sum of R matrices sitting at each point, right? But when you have a loop, then all the endpoints, they talk to each other. And in the 4x3 formula, there are many terms.
In a sense, if you are interested only in the Poisson bracket of functions which depend on one matrix, like if you want to write such
If it's a loop,
Mhm.
so then it's going to be this reflection equation, at least. But if the endpoints are different, this will be something like that.
I see.
So, but I mean, then over the years, people developed, like maybe that's something that I was explaining in the break. This machinery, it got developed very much, and there is, I think, maybe one of the refined versions is Leblanc-Severa, who explained how to decorate surfaces and boundaries. So I forgot, it's called quilted surfaces. They had some poetic word to describe the decorations, and then you would have some kind of refined theory how to deal with it. And in particular, they would be getting all kinds of gadgets like UQ of G, functions on G, the Dirichlet doubles, and so on. All right, more questions. Of course, right? This doesn't look all that pretty. Maybe that's why I thought maybe we should go into discussion a little bit of more conceptual things, and then I wanted to show you relations to other approaches. So that's my plan. We'll see whether there will be any DV structures, maybe just a short announcement of what it is about. So, right.
Sorry, one comment. In your reflection equation, don't you need the R prime in one of the side that is like exchanging 1 and 2?
No, but there are here minuses and pluses, right? Remember, I have two R matrices. One of them is exchange of R minus 1.
You already defined that is permutation of that.
Maybe I should. Let me
Yeah.
repeat. R minus is P.
It's just below.
Yeah.
If we could write it in terms of like normal R matrix, that is easier to see the relation with the classical version that we know, that then just one of the R is like R, like exactly the permutation of that. So we don't need to.
Well, I don't know. Let's say all of us have our deficiencies. That's the way I learned in the childhood. For me now, it's difficult to get rid of it. But yeah, sure, you can write it in many different ways. Of course.
Sorry, I actually have a question. So originally we're interested not in this home, but in its quotient by the conjugation action, right?
Wait,
And
yeah.
so,
Okay, sure. That we're going to
you'll discuss it,
about.
okay.
Yeah, that's we're going to talk about now. So,
Sorry, one last question. About the UQG from the start. The representations, are they built just like for classical algebras?
sorry?
For UQ of G,
Yeah.
for instance, for SLP, how are representations built?
Or you mean just in general for you to...
I mean, or just for SL2 already?
Okay, so like there are two different stories. The story that we are developing here, right? Deformation quantization, which means that H or Q may be like a formal, or Q minus 1 is a sort of formal parameter, or maybe some generic complex number that may be also possible. So then representation theory will be exactly the same as for U of G. So there will be, for SL2, there will be irreducible representations in all dimensions. Now, when Q is a root of unity, the situation dramatically changes, and that's the whole life apart, or actually many different lives apart. So there would be very complicated representation theory, many versions of it, so that we perhaps don't enter now. But in our case, they're just representations as for the ordinary Lie algebra. Well, of course, you need to deform them and say how they deform.
So I would take the highest weight, build up from E or F.
Sure. Yeah, you can. Yeah, sure. You can do that. And I think probably most of the quantum group books, they would do exactly that. Right. Okay. So and now this algebra, it gets split So you can define some sort of quantum Goldman map, GQ. Let me say how it's gonna operate, but I don't yet say what's the source of that map. So it would map a conjugacy class in pi1 as before into the trace of rho of alpha. But remember now, right? Alpha will be some product. I can represent it as a word in my generators. Now my generators, they map into some matrices whose matrix entries are generators of my algebra, right? So here actually I should slightly modify the trace. I should add some constant matrix which corresponds to the so-called quantum trace. And the element here will be an element of H. Moreover, it turns out that H here is an action of UQ of G. So that's the feature of the construction with those R matrices. And actually, this element is an invariant element under that action of UQ of G.
What was the low in the quantum piece?
Sorry?
What was the low on that?
So the quantum trace means that this is an ordinary trace, and you add, I think if I remember correctly, for instance, in the case of n equal to 2, maybe the knowledgeable people here will correct me. So you add, or maybe q1 half, q minus 1 half. So you add some constant matrix in the trace.
How about low? Low. Low.
Sorry.
The low map. The low of alpha. The low.
This one?
Row.
Row. Oh, okay. The row map. Okay, the row map we build exactly in the same way as before. So suppose that, okay, let me denote it by some other letter, let's say x. Suppose that x is alpha 1, beta 2, alpha 3 minus 1, right? So to each of them we have a matrix, in our case A1, B2, A3 minus 1. Of course I should explain what does it mean A3 minus 1, but okay. So, right, we multiply them, their matrix entries are elements of my algebra, right? So I get a matrix whose matrix entries are elements of H. I apply this, whatever, quantum trace, I obtain an element of H. So this quantum trace has a feature that this element will be invariant under the UQ of G action. Right? So in this way we obtain elements of our invariant subalgebra. Furthermore, similar to what we had before, right? We have a boundary loop. And here I start getting really approximate. So GQ of powers of the boundary loop, right? Before, remember, in the Goldman algebra, these were elements of the center, right? And this turns out to be in the center of H. So now I think the question was, how do we define quantization of the moduli space for a closed surface, right? Right, with this fancy boundary. So you artificially make a boundary component, and then the story above runs. Now, your quantum functions on G, this will be defined as the invariant part, UQG invariant part of H, and then you divide by the ideal where those images of gamma k are equal to some known constants. So that's basically you're fixing the center, and that's how you quantize a moduli space for a closed surface. So you see, it's sort of a little bit parallel. After you accept the four-crossly description, the story becomes parallel to what we've seen on the classical side. Of course, here I think I'm omitting relatively many technical details, making it maybe sound easier than it is. But honestly, like, maybe that's what I remember, and that's the positive things. The difficult calculations I don't remember. I want to spend a little bit of time talking to you about comparison of this scheme, or maybe mentioning other quantization schemes, right? Because moduli of flat connections has lots of quantization schemes. Some of them are related to this one, and some of them are relatively distant. So about some of them I at some point knew relatively much, about others not that much. So comparison to other schemes. So there is a story due to Roche and Senesh, and I think they're also using four-crossly as a starting point, but they're working directly with this gadget. So they don't want to go through H itself, because for that you need to introduce, either open the surface, introduce that base point. So their description then is more heavy, because they have to introduce some intertwining operators for quantum groups, which will be part of the business. That's because essentially they work directly with the right object, but they don't have a finite generating system as for pi1. So then another one, and here maybe Jürgen can say can add some words. So this is similar in spirit to what we were doing here, but as he mentioned, so as far as I recall, this scheme works with T. Remember, we had a choice with four-crossly. We could work with R and with a Poisson bracket, or we could work with T and work universally. So one advantage of this T, it's related to something that people like to do in knot theory. So this is the so-called chord, right? I don't know whether you heard of chord diagrams in knot theory, whatever. But there it's a kind of big business, very well developed. So one could capitalize on that, if I may say so. So, and then there is this famous from topology 4T relation that Jürgen mentioned. So, and this is indeed more universal, right? Because it works universally for all quadratic Lie algebras. So, Jürgen, do you want to?
No, I can just say that we developed that and showed there was a Poisson homomorphism onto the functions on moduli space for G with invariant bilinear form, as you mentioned, more general than killing, right? Mm-hmm. And then what we did was we considered, inspired by Tureyev, links in surface across the interval, and considered the Vasiliev vibration on that, and showed that that gives you a deformation quantization of this algebra, which also descends to a deformation quantization on moduli.
For any surfaces?
For any surface which has a boundary, a non-empty boundary.
Maybe a somewhat related scheme. I think it was maybe formulated by Liebland and Severa, and then recently completed by Pullman. You see, once you enter the game with this 4T relation, so then there is another story also which plays a role in knot theory that you can employ for quantization. That's the story of Drinfeld associators. In fact, to quantum groups there are several approaches, and Drinfeld even long ago developed several approaches. So one approach uses the choice of an R matrix, maybe first classical and then a quantum R matrix. But then there is another approach which is in some way more invariant, where you only use those T guys. And then, in some sense, let's say, it's not quite true what I'm saying, phi is a replacement of the R matrix. So that's the main quantum object that you are using. So it's more invariant, but the problem is that the associator is typically a lot more complicated object than an R matrix. R matrix is not quite symmetric, but then I even wrote an explicit formula for one of them. It's in the first approximation out of question. You can write sort of formulas for, there are some associators which are better than the others, and there are some sort of formulas, but it's very, very scary. But it's a lot more invariant. So I think they developed an approach which is probably, I don't know, that's a research project, but it's probably related to what Jon and other people were doing long ago, but it's all packed in the associator. So they define that quantization in terms of associators. So now...
Can I make a further comment on this? Because certainly, the big machinery we used, you're using the big machinery of quantum groups.
Yes.
The big machinery we used from knot theory was really Maxim's big theorem that there is a universal invariant. And so there, you can really actually take any associator in this universal language, and then that will give you a quantization of moduli spaces. And so that was sort of clear from our construction. But I think one thing that was sort of interesting from our point of view was that, or embarrassing in some sense, was that we had to use some structure on the surface, which was a hexagon decomposition of the surface. And we definitely get different quantizations depending on the hexagon structure.
Okay, here I cannot judge. I think Liebland Severa, they also encountered some choices that they couldn't fight with. And recently Pullman solved it. So he figured out the natural isomorphisms between, I don't know whether it's equivalent to your choice, but it sounds, I don't know, they maybe were using triangulations or whatever, some kind of finite combinatorial structure on the surface, and Pullman was able to get rid of it in some, associate theory.
Well, we utilized it sort of to get a representation of the Ptolemy groupoid instead.
But I think it is related. I can send you a link to his paper. I don't know whether it's whatever. But is it equivalent? But it sounds like it might be related. I still have 5 minutes. I want to list two more approaches. So
You have some time from the first half as well.
Oh, tempting, but okay, we'll see. So now there is another approach due to relatively recent, but by now not so recent. So Ben Zvi, Brochet, Jordan. So they used factorization homology, whatever it is. So it's some kind of advanced categorical technique which allows you, let's say, here we were talking about algebras, so generators and relations. And as far as I understand, but here maybe some experts in the audience can correct me, so they're targeting directly the category of representations of the resulting gadget. And so they claim, okay, they have a very beautiful notation. So you take a representation category of UQ of G and you integrate it over the surface. Whatever this might mean. But what is interesting, they proved this theorem that I don't quite know in which, like maybe with a boundary, probably with a boundary, that this is isomorphic to a representation category of this algebra H that I explicitly described before. This boundary, I think. So this is. So last but not least, or at least last among those that I plan to list here. Skein quantization. So skein quantization is the idea that you take the Goldman Lie algebra, the Lie algebra that you start with, and you try to promote it into an associative algebra by replacing all those resolutions of singularities by skein relations from Knott's theory, from John's polynomial, basically. So I think it was pioneered by, okay, there are many works. It was pioneered by Turayev many years ago. And so there is a recent paper, maybe of last year, of Constantino and Le, which, if I understand correctly, claims that the correct target, basically it says that the correct target of the quantum Goldman map would be skein algebra, and you would map it to this H invariant part, UQG invariant part of H. In the case, I think in their paper, it's in the case of n equal to 2. So basically, relation between all those different quantization schemes, they are all some kind of research projects. Some of them are accomplished. Some of them are probably still open. I'm not sure that it's known how to do this thing for arbitrary n. At least that's my impression from the discussions with Tankle. Maybe the last thing I want to tell you. So, in principle, that was all about Lie algebras, right? But in principle, there is a big chapter of life when G is a Lie superalgebra, right? That's another life. These interesting things, and here there is a choice between, again, two very different lives. So in any event, you probably want some kind of invariant pairing. And this invariant pairing may be even or odd. In the case, so there are interesting works in the case of even pairing, and maybe you can ask Nejla if you want to know more about it, because she worked out in that direction. And the pairing can be more exotically odd. And that's the third part of the lectures, which is not going to happen. And this leads, again, this is like the setup is very, very similar to what you've seen by now. The resulting structures would be not Poisson structures, but BV structures. So this is related to the so-called Turaev core bracket. This is a much less known kind of sister of the Goldman bracket. And to the best of my knowledge, here not much is known. Like on the Goldman bracket, as you have seen, right? And here I listed probably some small part of the developments. Like, okay, one doesn't know what would be the analog of R matrices, if any. One doesn't know to what kind of physics it is related, if any. One doesn't know what's the relation between this story and that story, even though they use the same structure, this Goldman-Turaev Lie algebra. So here there is really some kind of sea of open questions. In particular, probably this story should talk to that story of Skane quantization at least. And this is absolutely not known. I think it's a good phrase, right? To end the talk.
Okay, any questions? Maybe I could just finish the comment before. So I was saying that it depends on this triangulation of the surface, and so in a sense you would want to, remove that. But there was another place where we actually utilized the fact that it does depend. So you actually get what's called a representation of the Ptolemy groupoid on this algebra of chord diagrams. And one thing that was sort of funny was that if we truncated that to first degree, we were able to construct, a sort of a Torelli representation out of this. Well, rather the Johnson homomorphism, actually, the first Johnson representation out of this, and so that was kind of fun, actually.
So you were getting the first Johnson, whatever, filter.
Homomorphism, yeah, from this simply. So
that's the wrong week. The Johnson homomorphism week was the last week here.
Do you know if that factorization homology thing has to do with conformal field theory?
I think the answer is yes, but I don't know any details. Sorry.
But can you also use these RUU relations to quantize your what will you get if you use the RUU quantization? You get some moduli algebras or
yeah, you get. So maybe I was not clear before. So in general, when you have many base points, suppose you consider a representation of some fundamental groupoid instead of fundamental group. So you choose several base points. So then for the quantization of images of those guys, of polynomials along those paths with two different endpoints, then you would get this RUU equal to UUR.
it's okay.
So when you have different base points in the first approximation, I'm still cheating a little bit, but you get these functions on the group. But when you go to the same, when you return to the same point, you get UQ of G.
Is it there is like a discrete version maybe of this Goldman bracket, which is like the necklace-ly bracket on quivers, right? If you just think of it. And then you have the core bracket also there. Wasn't there something, what is it, like Travis Shedler had something about quantizing that, right?
Yeah.
Is this somehow in any, I don't know, in any way like a discrete version of this, like, is this relevant? Or because I know that some quiver varieties give moduli spaces of connections, right?
Do you want to answer?
I think Tarif did by quantization. He also have a co-product on it, so it's.
Okay, maybe I can say something. So this is related. That's basically related to the following fact. I didn't mention it, but in principle, there is the whole other dimension to the story. You can apply. You have a natural filtration on a Goldman Lie algebra. Right, and the associated graded, right? You will get associated graded, and your structures, in particular the bracket, will induce something on the associated graded. So that's a particular instance of necklace. Right. So then, indeed, you can quantize on both sides, and then I think it is known, right, Muse, that quantizations in the first approximation are isomorphic. The question whether biquantizations are isomorphic is still okay, probably, maybe getting of conjecture. Yeah.
For quantized square varieties, you mean?
Yeah, whether like skein biquantization of Tarif would be isomorphic or whatever would to the biquantization of necklace by Shedler, I think, okay, to the best of my knowledge, it's not known. But it's a natural conjecture, but whether it's true or not, I don't know. So, but this would be related all to some kind of filtration that I didn't talk about.
May I ask, is there any analogs of Fokker-Roswell formulas for the superalgebra case? What is similar?
You mean odd or even?
The first question is which of these cases have this analog of Fokker-Roswell bracket?
I guess all analogs, right? I don't know, right? I think so if it's even, I outsource to Nezla.
And if it is odd?
If it's odd, then instead of the, okay, instead the Fokker-Roswell, the Fokker-Roswell object, let's put it like that, it's going to be not a bivector, but a second order differential operator. And this second order differential operator will be a BV operator. So basically, like the two differentials will act on the same function, not on two different ones. Right, but I think for even, I guess you probably have as before, right? So the even story should be more similar to what I was talking about. An odd story is really a different one.
Let's thank Anton again for
This is good.